A thin rod is pinned at one end and dropped. What is the magnitude of the reaction force from the pin? So what's happening here is we have this thin rod of mass m and of length L, and as you can imagine, it's pinned at one end, and this bar is left to undergo circular motion because it's dropped in this position shown. And we're asked to find out what the magnitude of the reaction force on the bar is at this point. Well, the way you start solving this problem, just like every dynamics problem you'll ever deal with, is to begin with the free body diagram. Now, of course, because this thing is pinned at its end, that means we'll have reaction forces I will call Ry and Rx, right? And because this is pinned, not cantilevered, you won't have a moment, it's just forces. As you can imagine, this thing's free to rotate, but it's not free to move at this point, okay? Now, that's not the only force you've got on your bar. You've also got your force due to gravity, which will be mg downwards, right? Okay, now that our free body diagram is sorted, let's draw an axis so we can define what we mean by positive and negative. I'm going to use our standard Cartesian axis, xy just here, to denote positive to the right and positive upwards. Okay, now we're ready to start with Newton's laws. We know that the sum of forces acting on our bar in the x direction is equal to the mass of our bar times by our acceleration of our center of mass in the x direction. Let's break down these individual values separately. The sum of forces in the x direction will just be Rx. There's only one force in the x direction, and it's Rx, which is quite easy. Okay? Now what about the other terms? Well, our mass is our mass, but what is our acceleration of our center of mass in the x direction? In order to find this out, let's draw our bar again. And let's also draw our center of mass just here, and also this point, which I'll call point O, which is the point about which our bar is rotating. Now, as you can imagine, every particle that makes up this entire thin rod will be undergoing circular motion, including our center of mass. But let me just plot, at least at this instant, the circular path which our bar is swooping out at this instant, right? And as you can imagine, because our center of mass is undergoing circular motion at this instant, that means our acceleration in the tangential direction is alpha r, and our acceleration in the normal direction is omega squared r. Hopefully you remember this from circular motion formulas, right? And fortunately, this is quite easy to deconstruct into x and y components. We know that our acceleration of our center of mass in the x direction is just negative omega squared r, right? And it's negative because it's acting towards the left, and right is defined as positive. Now this turns out to be something quite easy to analyze. We know that because our thin rod is dropped, right, that the velocity of our center of mass is originally 0, which means that our angular velocity is also originally 0, which means that Rx is in fact 0. Okay, so far so good. A little bit of a boring answer, I know, but rest assured Ry will be a little bit more interesting. Now let's apply the sum of forces in our y direction is equal to MAGY. Okay? Well, what are our forces in the y direction? We've got Ry just here, but we've also got a negative mg. It's a negative because it's downwards, and positive is defined as upwards. And of course, this is equal to m, and AGY is just negative alpha r. Now don't forget, it's negative because this is downwards, and positive is defined upwards. Okay? And if we try and solve for Ry, we'll get a little bit stuck, and you'll see why. Ry will be equal to mg minus mr alpha. Okay? Now there's two things we don't know here. We don't know r and we don't know alpha. R is the easier one of the two to calculate. We know that the radius of our circular path is going to be this distance, which is L on 2, right? So R is in fact L on 2. So let me just write that in there. R is just L on 2, right? How about this alpha here? Well, we need one more equation to find alpha. And I'm going to use this equation. We know that the sum of moments about O is equal to I O alpha. This only applies if we're dealing with a pin just here, which isn't accelerating, right? So this formula applies. If you wanted to, you could have also used this formula. The sum of moments about our center of mass is equal to IG alpha. I'll leave that as a separate exercise for you, but I rest assured you will get the same answer. Okay? But for now, I'll do it the easier way. Well, what are the sum of moments about O? Well, if this is point O, we've got only one force which produces a moment, which will be this mg just here. And of course, the moment caused by it will be our force, mg, times our perpendicular distance, L on 2. So in fact, it's going to be mg times by L on 2. Okay? And that's going to be equal to IO. This is the moment of inertia of your rod about O, which will be ml squared on 3, right? And of course, we're timesing that by alpha just here. Okay? This is your moment of inertia. Hopefully you remember that from those videos. But if you don't, please feel free to look at my previous videos. Okay, well, we can solve for alpha here. Once we notice a few of these things get canceled off, we know mass goes like that, and we know L goes like that. So that means alpha is in fact, let's see, it'll be 3g divided by 2L. 2L. So that is in fact alpha. And we can plug this in here to solve for Ry. We know that Ry is in fact mg minus ml on 2 times by alpha, which we just figured out was 3g on 2L. And of course, this boils down into mg. Let's see, the L's cancel nicely. Leaving us with 3mg on 4 minus 3mg on 4, which boils down into 1/4 mg. So I'll write that this is mg on 4. That's going to be Ry. Okay? Now we're almost done. We found out our reaction force from our pin on our bar in the y direction and the x direction. What's the magnitude of the total reaction force from the pin? Well, if our total reaction force is written as R, we know that it's going to be the square root of Rx squared plus Ry squared, and this turns into something quite easy to analyze. This will turn into the square root of 0 squared plus mg on 4 squared, which turns into mg on 4. This is the magnitude of your reaction force just here. This is our answer. Phew, I hope that made sense, guys. Cheers.